continuing on with our right triangles, there's actually two situations that are kind of unique and pretty important for those of you who are going to be moving on to especially trigonometry and beyond, calculus and whatnot, because I don't know if it's the symmetry of these types of angles, but they're very quite common out in the real world and a lot of homework problems. Okay, but basically, to introduce ourselves to the first special right triangle, let's consider the following situation. I would like you guys to find the lengths, right, of the sides for the following situation. All right, and if you're having trouble reading, that's 7 meters, and that's a 45-degree angle. All right, so there's basically two unknown sides, right? So how about we just label this as B, and we label that as C to kind of be consistent with what we've been doing. And so if I tried using the Pythagorean theorem at this moment, right, the only thing I know is A, so we're going to have a tough time figuring out what's next because we don't know, right, what B or C is. That's what was kind of nice about the last couple of videos. We at least knew two of the values, and then I can use those to find the third. But right now I don't know two of them. So something strange is going on, right? We don't ditch the problem because there's actually something cool. All right, so let's go look at this right triangle. If this is a 45-degree angle and we know that's 90, can you guys tell me what that angle would have to be? Right, and hopefully at home you're thinking, well, that would also have to be 45 because the sum, right, of all my angles has to be 180. So 45 and 45 would be 90, and then plus that 90 would give me the total sum of 180, which is needed in a triangle. So that side, that angle would have to be 45. So if we just think geometrically about this or common sense about it, right, what would have to happen is if these two angles are the same, then that must mean that this side and this side would have to be the same, which would mean that B would have to be 7. And it turns out that that's actually the case. If these two angles are the same, then these two sides have to be the same. So that's good news for us because I can now go back to my Pythagorean theorem and I can now solve for C. So what we're going to get is 49 plus 49, and I believe that's going to be 9 and plus 9 is 18, carry the 1, 98. Take a square root. We've introduced a plus minus, and we're talking about the positive root of the square root of 98. Of course, 98 is 49 times 2. So C is 7 square roots of 2. All right, and so we basically have solved that right triangle by using kind of a, we used the Pythagorean theorem later, but we really used a geometric coincidence or geometric certainty, if you would, to solve it. And something that's very interesting, notice that this side here, right, is equal to that side there, and then even the hypotenuse, even though it's not equal, it still makes use of that side. It's actually the side times the square root of 2. So when we look at any 45, 45, 90 triangle, and that's what kind of triangle we have here, 45, 45, 90. So both angles are 45 degrees, and if this side is length x, that means this side is length x, which means that this side would have to be whatever x is times the square root of 2. And of course the proof of that is if this is true, it should satisfy the Pythagorean theorem, right? So we have x squared plus x squared, that should equal to x times the square root of 2 squared. Well, x squared and x squared is 2x squared, and then here we have a power of a product, so if I square the square root of 2, we get 2, and if I square the x, I get x squared. So you can see that it is a mathematical certainty now. We know the Pythagorean theorem is true. We came up with this hypothetical relationship between the sides of a 45, 90-degree triangle, and the Pythagorean theorem says, yep, that's true. That's a true statement. So that's good news for us because we can just basically use this pattern. Okay, so we don't even need the Pythagorean theorem anymore. We just recognize the pattern. So here's what this is going to look like. So I'm looking at this triangle here. I'm asked to find the lengths of each side. So it looks like we're given B. I don't know what A is, and I don't know what C is. So again, we're stuck. We don't know two sides. However, I do know this is a 45-degree angle, which forces that to be a 45-degree angle. So we have a 45, 45, 90 situation. What does that mean? Well, this side and this side have to be the same. So I know that this side would also have to be 5 inches. And then C is that 5 inches times the square root of 2. And there would be your solution. So in this case, A is 5, C is 5 square roots of 2. So it's a pretty easy situation to work with once you see it. Making it a little harder, the next situation, again, I have a 45, 45, 90. So we know that that's 45. So we know that this side and this side have to be the same. The only side we're given here is 50. 50 is 25 times 2, and that is 5 square roots of 2. And so what that basically tells me then, this is coincidence, I probably should have done a little better. Not all right triangles are equal to 5, okay? But since this is 5 square roots of 2, this means this side's 5 and this side's 5, right? And we're talking feet here because of the measurement there. So I apologize. I should have maybe used like the square root of, I don't know, 98 like I did over here, right? And that would be 7 and 7. But I hope you guys get the idea. So again, we're making use of a pattern. A 45, 45, 90 right triangle has a very unique, very special pattern that we can take total advantage of. And we did in a couple situations, actually 3 of them. All right, so another special triangle coming up. We'll do that in the next video.